Alright, so we're going to do problem 3 out of Rosenlicht's Introduction to Analysis. This is from chapter 1, and it's a problem about sets. So we have A, B, and C are subsets of some set S, and we want to prove a bunch of different statements. So for this first one, A, the complement of A union the complement of B is the complement of A intersect B. So we have that these are subsets of some set S, and if we think of this as like A and B, well, then the complement of A is going to be everything that's in this green. And the complement of B will be everything that's in this red. So if you just look at the picture, the only thing that's not highlighted is the intersection. Thus, this will be the complement of A intersect B, like the statement says. So let's see how we would write this out. So to show this, we want to first show, step 1 would be to show that the complement of A union the complement of B is a subset of the complement of A intersect B. And so how we do this is we can say let X in the complement of A union the complement of B. So this tells us, so either X is not in A or X is not in B. And we want this to imply that X is not in, if X is in the complement of A or X is in the complement of B, X is not in A or X is not in B. Well, so what we can do here is we can say, without loss of generality, say X is not in A. Then X is clearly not in the intersection of A intersect B, because if X were in the intersection, then that would imply that X is in A. So X has to live in the complement of A intersect B. So that shows that this is a subset of that. But to prove equality, we both need we need the other subset. So now we want to show that the complement of A union the complement of B is contained in the complement of A intersect B. So to do this, we could write, say, let X in the complement of A intersect B. So what this means X is not in A intersect B. So we want to show that X is either not in A or X is not in B. And this is clear since if X were both in, if X were, so if X is not in the intersection of A and B. So if we do, say, for contradiction, if X is not in the complement of A union the complement of B, so if X is not in here, then we must have that X is not in the complement of A or X is not in the complement of B. So say, give me a second to think about this. So if we're going by contradiction, if x is not in the union of the complements, then it's not in the complement of A, it's not in the complement of A, or it's not in the complement of B. And we're also so the contradiction shouldn't be that so I have the right thing written down. Sorry about that. So we're assuming for contradiction that x is in the complement of A intersect B, and x is not in the complement of A union the complement of B. So what this means is, this means that x is, well, if you're not in the complement of A, that, or x is not in the complement of B. But if you're not in the complement of A, that means you're in A. So this means that x is in A, or x is in B. Because if you're not in the complement of A, then you're in A, and if you're not in the complement of B, then you're in B. So if x is in the complement of A intersect B, and we this should, since x is not, so this should be an and, not an or. So the reason being, if x is not in the union of these two, that means it can't be in the complement of A and it can't be in the complement of B, because if it were in either of these, then this would not be true. So this implies that x would have to be in A intersect B, but we said it's not in A intersect B, so that's the contradiction. So that's how you get this, or one way you can write this out. So now for part B, so let's draw our Venn diagram to help us out. So we have three things, say I'll call them A, B, and C. So if we're looking at what A intersect B union C is, so B union C is this. And so this is B union C. And if we look at A intersect B union C, it's going to be this. So this will be A intersect B union C. But we also see A intersect B, so A intersect B is going to be this part here. So this is A intersect B. And if I use pink, and A intersect C is this part here. But if you look at the union of, so that's A intersect C, this part and this light blue and pink, that's exactly the red, and that's why this equality is true. But if we want to write down the proof, so the first thing is we want to show we have this inclusion. So we can say let X in A intersect B union C. So what does this mean? This means that X is in A and X is in B, or X is in C. Because you're in A, and you have to be in the union. So X is either in B or in C. But this just means that X is in A and x is in B, or x is in A and x is in C. And that this just means that x is in A intersect B union A intersect C. And so all of these statements are actually if and only if. So if you read going from top to bottom, that proves this inclusion. But if you start at the bottom, this proves this inclusion. So if you start off with x in this, well, that means x is in A and x is in B, or x is in A and x is in C, and then you go backwards. So that proves this inclusion, and that gives you the equality. Alright, and the last one is we want to prove this statement, so let's draw a Venn diagram again. So say we have our circles A, B, and C. So we're doing A union B intersects C. So B intersects C. B intersects C is this. And we're just going to add A, which is this, on top of it. So this whole thing is, so that whole thing is A union B intersects C. And we want to show this is A union B intersect A intersect B. So A union B is all of this. So this is going to be A union B. And let's see, here's brown. So A union C is all of this. And notice they both have A in common, and where they intersect besides A is this slither right here, which is exactly what A union B intersects C is. So that's kind of the pictorial idea of this. And if we want, we can do a similar thing as last time. So we want to show both inclusions. So if we have x is in A union B intersects C, so this means x is in A, or x is in B and x is in C. So if x is in A or x is in B and x is in C, this is the same as saying x is in A or x is in B and x is in A or x is in C. So the reason why these two are equivalent, so all of these are logical equivalences, and this will just tell us that x has to be in A union B intersect A union C. So the reason we have this equivalence here is if x is in A or x is in B and x is in C, well, if we have some element that's either in A or it's in both B and C, then this element has to either, it's either in A. And in the case that so if it's in A, then we're good. We're in A and we're in A. But in the case that we're in B and we're in C, well, we're in B here and we're in C here. So we're good. So that's why this is a logical equivalence. So this shows this equality, and that finishes the problem. Thanks for watching.